Hello, my name is Alberto Marin, and I'm doing a thesis about plasma-wall interaction, and my supervisors are Eduardo Aedo and Adrián Domínguez. So today I'm going to bring you some updates that I have done over the last year, and I'm also going to review how the thesis is going and the things that we have already completed. Okay. So first, a brief introduction, which is about Hall effect thruster once again, and we know that this is the leading technology in the electric propulsion sector. But we still have some open problems. I'm not going to go through all the details because we have already had some talks about the Hall effect thruster. So let's move on to what happens at the wall. Well, we have three different species, which are neutrals, ions, and electrons, and each of them react differently to the wall. So neutrals just bounce back and are reflected, so nothing dramatic happens there. Ions get recombined at the wall, so we have lost plasma, and then we have electrons. Electrons, depending on the energy with which they reach the wall, they can be collected or they can emit secondary electrons from the wall. So they can extract electrons from the surface of the material. Okay, this is a phenomenon that can happen and can extract one or multiple secondary electrons. So why are we interested in plasma-wall interaction? Because if nothing happens, we are not interested in studying this. Well, it's very important because it implies energy losses. It also implies ion recombination, so we are losing plasma, our thruster is not going to work. We have also wall material erosion, so it's important for the lifetime of the thruster, and it's also responsible for a phenomenon which is called near wall conductivity. Okay, this is also something that could lead to anomalous transport, which is the topic of Enrique, although we believe it's not very important, but it's also there. So, in order to study this plasma-wall interaction in a Hall thruster, we need to solve the plasma dynamics inside the Hall effect thruster. But we have seen, and we know that the plasma inside this Hall thruster is weakly collisional. Okay, this means that there is no need to be thermodynamic equilibrium. This means that we require a full characterization of the species velocity distribution function, which means that we are going to use a kinetic method. Okay, but kinetic study of plasma is very computationally expensive. As Enrique has commented, we have to resolve very small length scales, time scales which are really small, so this is very computationally intensive. Let's do also a review of the different methods that we can use here in order to simulate plasma. Okay, the final goal is getting a nice description of what's happening inside our Hall effect thruster, and we have in kinetic models, we have a fully kinetic model. Okay, we have fully kinetic, which is just solving this equation, but it's a very high dimensional equation because here we have gradients in the velocity space and the physical space, so it becomes complex when you go to high dimensionality. You can also go to a particle method, which is what we are exactly doing, which is basically discretizing these equations in terms of particles and moving them. And the third option is say, okay, I'm not going to solve exactly this equation, I'm just going to solve integral moments of this equation, which is basically the typical fluid dynamic equation. This is going to be this Navier-Stokes like. Okay, but the problem with this is that you will never get a closed set of equations. You will always have to make some assumption in the velocity distribution function shape. And this is why, okay, it's a good approximation, it's fast, but we are missing something. So this is the thesis plan. So we started with this problem of wall interaction in a 1D radial geometry, which is simple. Then we move on to a 2D scenario, which for that we are using the code that I'm developing with Enrique. And then we are going to check if the assumptions that we made in the 1D model hold. How are the axial dynamics affecting the plasma wall interaction, and try to characterize these fluxes to the wall. Also, we want to analyze complex magnetic topologies, but this is ongoing. And we have noticed that plasma wall interaction is not only important for electric propulsion, it's also very important for fusion plasma. So we are going to do a research study with people at PPPL, which are doing this, but for fusion plasma, and we are going to see if there are similarities or not. Now, let's move to the simulations of the Hall effect thruster that I have just done in some months ago. So we are going to take this slice of the Hall effect thruster. We are assuming axis symmetry. These are the boundary conditions. So here we have the anode, which is electrically connected to the cathode. We have some electrons coming from the cathode to match currents, and we also have the interaction with the walls and everything else. We have a perfectly radial magnetic field, which, although we know it's not 100% true, is a good test case for us. And it follows this profile, okay? We are assuming that it is externally imposed, and we are neglecting any induced magnetic field which can be generated by plasma current, because we are under the electrostatic assumption, and we're self-consistently resolving the electric field. Then we may move a bit on the model, and we are simulating here particle electrons and singly charged ions. We are using a fluid description for the neutrals. Collisions are only going to affect electrons, and we are going to have ionization because it's the only source of plasma. We're generating our plasma through ionization. And then we have some anomalous electron diffusion, which is going to do the effect of the correlative instabilities which generate this anomalous transport that Enrique has just commented, okay? These are the numerical simulation inputs, which I'm not going to go very into detail, but here you see that if you do the product of this, multiply it times 20 times 10 millions, you can imagine that these simulations take a long time, and indeed it takes more than 20 days to get the final steady-state solution. So let's look at the results, okay? This is first the density, which lies inside the range of density that we would be expecting. Here you have a generation of plasma due to ionization, and then it expands downstream. If we compare the electron and ion densities, we see that practically they are both equal, because this neutrality goes to zero, except in very thin regions very close to the wall. It is also in those regions where we find very steep potential gradients, as we would expect because of this formula, and this is the characteristic shape of device sheaths, which is a very well-known thing that happens very close to the walls, okay? You find regions with very high non-neutrality and steep gradients of the potential. Here we also have the temperature map, which is almost constant in each axial section. We don't have much radial variability, as one would expect, and the peak in temperature is very close to the exit of the thruster. So let's talk a little bit about what does the different species. Here we have the electrons, which, as I said before, were inputted through the cathode, which are all these boundaries, and flow towards the anode, okay? For ions, it happens the opposite thing. They get generated and flow downstream, but they also get accelerated towards the wall, and some of them even reach the anode. What happens with the total current, which is the addition of the two of them? Well, we know that at steady state, walls cannot correct net current. So this total current must be perfectly parallel to the wall. As you can see here, this is perfectly matched in our simulation, so we are happy about this because it means that at least we are not breaking the physics law. Okay? Let's compare a little bit these new results with the ones that I showed you in previous doctoral meetings and the one that we got with the previous 1D code. Okay? The previous 1D code was created in order to simulate the plasma within the acceleration region. Where is this region? At the end of the thruster. So it would be like this part over here. So we can take the results with the 2D code and try to compare with those. And more or less there's a good agreement. There are differences, of course, because we have now added axial transport, but there is not a dramatic change over here. What happens close to the anode? Well, we cannot extrapolate these results to here. This is totally different. Furthermore, if we plot also the Maxwellian velocity distribution function, which is the theoretical assumption, we see that it is completely off. So there are many other things going on close to the anode. Let's analyze a little bit what happens close to the wall, because we know that, okay, the most intense interaction with the wall happens in this acceleration region, which is where we built our previous model, and of course is the most important region. We have seen here that we have a large amount of secondary electrons, so those that were extracted from the wall. And these electrons are very bad from the point of view of energy loss, because these electrons are much colder than the electrons coming to the wall. So in the end, the secondary electron emission is trading hot electrons by cold electrons. So in the end, we are losing a lot of high temperature electrons and we are getting them replaced by cold electrons. So it's not good from an energetic point of view. Then we have that the main wall interaction parameters are not that off from those that we were expecting, taking into account the previous results, and close to the anode, so in this region is where the difference starts to appear, and we will have to analyze that. There's also differences between fluid and kinetic, because the assumptions of these do not perfectly match those. So in quasi-neutral electrofluid models, we have a Maxwellian electron velocity distribution function, or this is the typical assumption. We neglect electron inertia, we consider a scalar pressure, and we consider a Fourier law as the heat flux closure. What happens for kinetic? None of this holds anymore. And also, for wall interaction, there's a huge difference because only high energy electrons can reach the walls. And that means that if we're just assuming a Maxwellian distribution function, we're not going to capture well the wall interaction parameter. Now, let's move a little bit off topic. Let's make some macroscopic balances here. This is, I think I'm running a little bit late. Okay. Okay, so this is just a check that the axial current must be constant in each section. So here I have done this test just to see if I am resolving correctly the equation that should hold. So in the end, even if the electron and ion current do change along the axial direction, the net axial current is conserved. Okay, let's try to check the assumptions that we made in the 1D code, okay? This is the previous model that we did, and previously we said that, okay, the current that is generated by ionization directly goes to the wall. There is no other effect in this equation. So we were missing this axial term over here. So we can now take our 2D results and check if this is true or not. As you can see, in this last region, which is where the 1D model is supposed to work better, this is more or less a fair assumption, but here, it is for sure not. Okay, so we will analyze this a little bit more in depth in future works, and also we can do the same thing for energy. Okay, we can calculate the different contribution to this macroscopic electron energy balance, and we see that this energy, instead, the axial flux of energy, is a very important contribution to this balance. And indeed, this is one of the main limitations of the 1D model, because we are missing this. It's a very questionable assumption because it is of dominant order in this region of the end of the thruster, and probably that's why we couldn't control the temperature when we were attempting to do that previously. Just a brief summary of the things that we have done. We have seen two regions, one which is more explored and with results that more or less match the ones that we were expecting, the ones that we get with the 1D code. And then we have another region which is less explored, and we find a highly non-Maxwellian electron BDF, and things start to change over there. So it will deserve a more careful analysis. Future work will focus on simulating with a more realistic magnetic topology, since we have seen in previous work that it's going to affect a lot the velocity distribution function of electrons and also the wall interaction parameter. And we're also going to implement other collisional processes because, of course, plasma is weakly collisional, but still collisional, so it will have some effect. These are contributions to conference and workshops. This is 2 papers, and we're now going through the internal revision of this third one. And that's everything from my side. So if you have any questions, now you can ask.